It's a great honor to be here at this splendid symposium, seeing all the young stars here. It's a real delight. And so I was asked to talk a little bit about molecular nanoscience, and I will talk about the art of building small and try to put a little bit in perspective what it means that we and several others around the world are doing, and maybe prospects for the future. So we should not forget, being a scientist, the most important thing is the joy of discovery. And several of you, maybe most of you, will become scientists. Don't forget that. An adventure in the future means that we go apart towards our future with many challenges for all the young stars here. Dreams for our people and opportunities for our communities, our countries, our industries. But the most important thing is, as we heard yesterday, what question are you going to ask? And of course, often we get lost in this beautiful garden, which is the garden of science, and we get up questions that we have never thought about, and that often gives the most impressive discoveries. I often get the question, why do we need nanomotors or nanomachines? And so I go back to the Wright brothers, more than 100 years ago in the early days. And you know, they were for the first time flying with an artificial machine. And although for thousands of years people have been trying it, they were the first. Nobody would have thought that 100 years later we would build an Airbus or a Boeing 747, of course. You know what they asked to the Wright brothers? Why do we need to fly? If God wanted us to fly, He would have given us wings. This artificial machine, although we admire the flying bird, is completely synthetic. 3.5 million parts made by chemists, physics, material scientists, engineers, computer science, etc. And of course, the flying principle is not the flying principle of a bird. I would not have been in Stockholm. So it does perfectly what it should do. Carry 400 people across the ocean, 1,000 kilometers an hour, 10,000 miles across the ocean. Try to do that with a pigeon. You will completely fail. But we should also be very modest, because 100 years after the Wright brothers, we can build this machine in Europe, but we cannot build a pigeon. My friends in biology, I challenge them all the time, they cannot build a single cell of a pigeon. They cannot build one of the machineries of the cell of the pigeon. So we should be a bit humble. And there is a lot to be discovered. We should not forget to ask fundamental questions. And you might sometimes forget, you all have a smartphone. What were the fundamental discoveries that made that possible? Which fundamental scientific questions and insights and discoveries? I think many here of you cannot imagine that there was a world without smartphones. It's only 12 years. And you know, the discoveries were made in the late 40s and early 50s by physics and chemistry on transistors and display materials, etc. And nobody knew that we would have a smartphone. The world did not exist. They were just building the first computer. And so it was physics, chemistry, engineering, computer science, and many others that after a 50-year journey made the first smartphone. From fundamental questions to a route that completely changed the world, the way we communicate. So in chemistry, I'm a chemist. It's called often the creating science, and I'm typically making things, molecules, materials, like Professor Yagi showed and like Professor Arnold showed earlier. Making things, modifying things. So, how are we going to make the new sustainable processes and the products in our future to sustain our society? How are we going to fly in the future when there is no kerosene? How are we going to change the face of our chemical industry to be much more sustainable, lower energy? Or how are we going to make new medicines instead of trial and error, precision therapy? Fundamental questions and a lot of challenges. So let me first start with giving a little bit of credit to my teachers, because the fact that I studied chemistry was due to this man, my chemistry teacher in high school. And I'm sure you all remember one good teacher. That makes the difference. This was the man who made the difference in my life, because he made me so exciting about chemistry. The beautiful colors, the crystals, the ugly smells. the beautiful things that you can discover. This was my professor at the University of Groningen. This was actually the first molecule that I ever made. When I was 20 years old, a new molecule. Professor Winberg, who was American, said to me, this molecule has never been made, not even by our colleagues in America. I was so proud. It was an absolutely useless molecule. But it made me so proud, like making your first goal in the soccer team, or making a piece of music, or a poem, or whatever. So, I want to give credit to the teachers, because teachers, don't forget that. I also had occasions where I hated my teachers, making it too difficult. But never forget, they open the window for you to the future. So, I'm building molecules with my students. We do chemical synthesis, and in the laboratory, we built our own molecular world, more or less. And we developed a passion for building molecules. Like this molecule, Joseph, Professor Mikkel will recognize this. We build molecules simply because we find them beautiful. You might ask me, what is a beautiful molecule? We can discuss this later. It's like a painting, eh? Or a molecule that we test a theory, or it has a certain function, like a catalyst or a drug. But we could not have built any molecules, wasn't it, for the periodic table? And I want to give today homage to this person, Dmitri Mendeleev. In 1869, he came with the first periodic table of the elements. And this year, the UNESCO declared it the year of the periodic table to celebrate this. And we should put Mendeleev in the same category, I think, as Newton and Einstein. Why? Because the periodic table tells us the relation between all the atoms and molecules in the universe, including everything in your own body. And so, we know now that this smartphone has about half the periodic table. Don't forget that. There's a lot of elements in there, in your smartphone. But there is also a problem, because half of these elements suffer a problem in the future, because we use so many of these precious elements for all kinds of applications, from catalysis to electronics. So the better periodic table is this one, where you see now in green the elements which are omnipresent, but in red and in other colors here, all the endangered species. We were talking about endangered species. This is endangered elements. And so there are many elements that have serious issues. So please consult also this periodic table when you look at the future. So we build molecules and materials in the laboratory, and it's indeed a great privilege to work every day with these young stars. We share a universal language. This is great, seeing all of you. I don't speak Swedish, I don't speak Chinese, but when I go to China or to Sweden, everybody understands that this is the molecule of sugar. We have no borders. We go beyond borders. There's a lot of talk about borders these days. Scientists go beyond frontiers into the future. We have international cooperation, and we share a passion for discovery. And I want to share a little bit with you today. So we as chemists make typically small molecules and big molecules. Look, 2 carbons and 4 hydrogens, the basis for plastic, and we can discuss later if it's good or bad, all this plastic. Small molecule, 160 million tons a year. Or a very complex molecule, look at this one, built for the first time by Woodward and Eschenmoser, and it was called the Mount Everest of synthetic chemistry. Carbon, hydrogen, oxygen, many elements. But you need only microgram quantities to keep healthy. And we produce, as far as I know, only 35 tons a year in the whole world of vitamin B12. Very complex, very simple. Huge scale, small scale. This is what chemists do. So we make the cables in the cars, the fuels, the paints. We make the drugs, the dyes, soap, all the components of your smartphone. Not in isolation, of course, but together with our colleagues from material science, physics, the engineers, pharmaceutical scientists, etc., the biologists, that makes that possible. This is what we are good at. But what we are not good at is making anything that moves at the nano scale. Look, this is a rotary motor in your body. This is a bio-nanomotors that make things propel in your body and move things, transport things in your cells. This is the ribosome. This is by far the most ingenious robot that I know that exists. This one is fantastic. Look, this is a bacteria flagella mode. It makes the bacteria swimming in your guts. It can move forward and backward. Isn't it beautiful? This is the optical switching in your eye. It's a tiny machine. But we should not forget that this whole idea about building molecules, nanotechnology, tiny machines, started after Richard Feynman, a very famous physician, said there is plenty of room at the bottom. That was a quote in 1959 at a very famous lecture I think he gave in Caltech. What he didn't mean is go to the basement of this building. What he meant is start bottom up, like nature does it in the green plant, in your own body. Building with atoms, small molecules, bigger molecules, etc. We all know that in electronics, for instance, we have gone from large to small, top down. This was the first computer that filled half this room and could do way less than your smartphone. Now we had nanoscale dimensions. Bottom up. And it took again 50 years before we could make the first tiny motors and machines. And I had the privilege to go to Stockholm, and I lectured in this hall together with Jean-Pierre Sauvage and Sir Fraser Stoddart. Just to put it in perspective so that you don't forget, 1 nanometer is 1 billionth of a meter. So I take one hair here. You see it here, one hair? It's only one of my, I look, you have more hairs. Huh? So one hair, and if you cut now this hair on this cross-section of the human hair, you can put, it's 80,000 nanometers. It's huge in the dimensions of molecules. This is the dimensions we talk about. You might say, does it make a difference, size, if it's small or big? Yes, you all know that. When you go to a pebble beach here in Sweden, you don't drop on the beach, eh? It hurts. Yeah? And when you have a pebble in your bathsuit, you take it out because it's not so nice. But when you go to the north of Holland, where I live, you have these sandy beaches. Unfortunately, we cannot go too often because it's almost always raining. But we have this beautiful sand beach. You can drop on the beach without any problem. It's so soft. And when you take a shower in the evening, these fine particles are everywhere. The same material. Exactly the same material. So yes, do you find nano products? Yes, we find them in the sunscreens. You see, nano-sensitive. It's just tiny particles. It feels really good because of the tiny particles. It's also a bit expensive. Okay, you see quantum dots, 6 nanometer, 2 nanometer. You can make this very high definition color screens for TVs. This is what you can buy now in nano, in the supermarket. But this is all hard materials. What about soft materials, like in your body, these machines and motors I'm talking about? There I want to give a few examples of what is the future and what we have done. So we started many, many years ago with a simple idea. Can you do information storage computing at the molecular level? And you know how a transistor works, or information storage. You need 0, 1, 0, 1. And it should go back and forth. What is the most beautiful system that I know? It's not your smartphone, it's your eye. There are molecular switches in your eye, and here it is. Look, this is the retinal. It switches from a band state to a linear state. This is 0, this is 1, and it goes back and forth. This is the molecular switch. The fact that I can see you and you can see me is due to millions of these switches in your eye. And of course they should go back, eh? Because if they don't go back, I see you only once and then it's over. Now you might ask, when you started 30 years ago, why didn't you take those molecules from the eye and build a computing system or an information storage system? But of course you realize these molecules in modern nature are way too sensitive to build a transistor or these kind of things. So we had to make artificial systems, and we built these molecules so robust that we could switch back and forth with light. So you can store information using light and maybe do light-based computing. That's a bit a prospect for the future. We could build materials like a compact disc, or we could build all kinds of electronic systems based upon these molecular switches. And to give you a small impression of what nanotechnology can do is if you have a compact disc and you could store information at the molecular scale, you can store these megabytes. That means 240 years of music. Your grandchildren and your grandparents for 6 generations can use one compact disc, constantly play music for 240 years. That's the promise. That's not reality. You know why? Because after 30 years, we have not learned how to address each individual 0 and 1. Yes, we can do that, but then one of the molecules is here and one is outside the building on the nano scale. Because you have to separate, that has to do with the light you use, the wavelengths of the light, red, blue light. So please help me, because I'm struggling with that. And I know you are all very bright. Can you come and after the lecture, can you come to me and come help me with this problem? How you can do this when they are all very close together and you want to address individual zeros and ones? I think nobody in the world at this moment knows how to do that. If you have a great idea, don't keep it only for yourself. So we also use these switches. Once you can switch something, we thought, can we make smart drugs, pharmaceuticals? When you go to a doctor, you want to have a medicine that is active and that does something. We want them to be inactive, and we want to switch it on with light. So we take light, and if you have, for instance, an infection here, you switch it on with a lamp. 0 is off, 1 is on. And then maybe we can do precision therapy. Why do we want to do that? We work on 2 important problems. For instance, bacterial resistance, which was called one of humanity's ticking time bombs by the World Health Organization. Climate change is a serious problem. We all know that. We have to do something. We talked a lot about it. But don't forget, 1.6 million people die every year, twice the population of Stockholm, only of tuberculosis. And there are many other infectious diseases. And if we don't do something about antibiotic resistance, we will have a serious problem in the future. So we have to come up with unconventional approaches. Fighting this. Cancer treatment. You all know the nasty side effects of chemotherapy because it's not very precise at this moment. So we built antibiotics. We took an antibiotic from the clinic, built in a light switch, and what you can do then is switch on and off the antibiotic activity. Off, on, with light. And you see you can grow bacteria yin-yang. Here the bacteria don't grow, here they grow. Because we cover part, we irradiate, and where you irradiate, the bacteria is killed. And after 48 hours, 2 days, the bacteria grow normal. They don't build up any resistance because it's switched off again automatically. This is a bit the bio-nano future. And to put it in perspective, yes, maybe in the future we will have nano-robots. I will come to that in a second. Maybe the DNA technology, it was mentioned many times, and you read about it in the newspapers all the time, gene editing. This is not the metro of Paris or London, the underground. This is just a tiny, tiny piece of the biological complex network in your body. This is responsible that you don't bleed to death when you cut your finger. You see, smart imaging, photopharmacology, or rewiring the brain. Think about these possibilities that will occur in the future. And you all will be confronted or maybe do important inventions in this area. How are we going to live in the future when you get chips implanted and your brain is maybe rewired? There are also very interesting ethical questions we can discuss later about this integration of robotics and biology. So this is nanotechnology in the perspective of medicine. And there are many other aspects, of course. But let me talk a little bit about molecular motors. Because we started with these switches, back and forth, but then we developed a molecular motor. And you all know that here, this is moving. If things are alive, they can move. If you ask a little child, is it dead or alive? The first answer will be, oh, it's moving, it's alive. Because a biological system is not in equilibrium. It's out of equilibrium. If you read, or your teacher tells you, be in equilibrium, please don't. Be in harmony. But don't be in equilibrium, because if you are in equilibrium, you are dead. A biological system is not in equilibrium. So this is the most fantastic motor that I know. It's in your body. It's the ATPase rotary motor. It's a nano motor, a few nanometers in size. And it produces the fuel in your body. And if you are 60 kilograms, think for a moment, I learned from my biology friends that it produces every day, every 24 hours, half your body weight, 30 kilograms. Now, I appreciate your lunch, but I don't eat 30 or 40 kilograms a day. Neither do you. But it is recycled all the time in your body. So millions and millions of these tiny nanomachines make this fuel in your body, kilogram quantities, half your body weight. So, what is the problem we had to face when we had to design a rotary motor? That is how to control left and right. Imagine you have a car and you go equally left or right, you stand still. You wouldn't get anywhere. You have either to go this side or this side, backward or forward. How are we dealing with this problem? Now, you had this all in school. You take either a left-handed or a right-handed molecule. And the most beautiful example is DNA, the right-handed helix of DNA. So you can distinguish left and right at the molecular scale. And this is essential for life everywhere. It was called the Mona Lisa of modern science. And I think we can agree on that. So yes, we made molecules that are only left-handed or only right-handed. And then when we power them by light, it rotates. And it spins 360 degrees continuously, as long as you irradiate with the light. How is that possible? Now, it's possible because you put in the energy of the light, like in your eye. And instead of switching, it rotates. And we found it more or less by accident. 10 years after we worked on these switches, my students came and say, hey, it does not switch back. And then I said, this is not possible. And then we did a lot of studies and we found that it was rotating, it was spinning. Instead of going back, it was going forward. And that was the basis for a rotary motor. The first motor we ever built, this one here, is 1 nanometer in size, 1 billionth of a meter. And it rotated once an hour. That's not much of a motor, If it's only once an hour, you cannot build a car or you cannot do anything with it. But then we speeded it up, and my students learned by modifying the molecules to make it now rotating 10 million times per second. So we can control the speed at the nanoscale. Now, when you have something like that, it would be beautiful to see something rotating. And I want to share with you a moment in 2005. This was 6 years after the discovery, 2005, when my students came to me and said, this was the end of the day, we have to show you something. And this was the eureka moment for me. Because for the first time, I saw something moving with a nanomotor. What they did is, they took the liquid crystal material from your display in your smartphone or for your laptop or your flat screen. And this is this material, soft material. And they put a glass rod, as you can see, and this nanomotor is only 1 nanometer. You don't see it, because this is 10,000 times as big. And then the students switched on the lamp without touching. And this is what you see. So you see the color changes, the whole surface changes, and it spins, it rotates. And you see it rotates clockwise, in one direction. You can also rotate in the opposite direction. This was for the first time that we saw with the naked eye moving things autonomously, without touching, by a molecular motor. Then we went on and we built a windmill park. You know I'm from the Netherlands, and we like windmills very much. And these were built by our ancestors 500 years ago. And so we built these nano windmills, billion times smaller, on the surface. And it took us 10 years to prove that all these windmills are on the surface and they all spin in the same direction. So now we have a surface with nano windmills. And you might ask, so what is that good for? Why do you do these things? Why do you have to move something at the nanoscale? But realize now, people around the world are working now on self-cleaning windows, on solar panels that clean themselves, on cars that clean themselves. This is the future. In China, they produce now the first self-cleaning windows. Isn't it cool? Solar panels is a real issue, eh? Maybe not in Sweden, certainly not in Holland when it rains a lot. But in south of Spain or in the Sahara or in California, you have to get the dust all the time out of these panels to clean them, otherwise the efficiency goes down. If you have coatings, surfaces that can change behavior or repair themselves. Several people around the world, several groups work now on self-repairing, self-healing materials. And when you cut your finger, it heals itself, eh? But when you have a scratch in your car, you have to go to the garage. I think in 10, 15 years, we will have these examples of these materials that heal themselves. And groups around the world have made already the first self-healing materials. This is a big development. Learning from Mother Nature and translating it into artificial materials with all kinds of functions. We built also a nano car. You see, my students were a little bit jealous of the engineers that can go to this car race. I don't know if you read about that or saw this on television. These engineering students, they go to, also I think from Stockholm, they go to Australia and they do this car race, this competition in the desert. And they can go 3 weeks to Australia. My students said, can we also do that? I said, look, we are not engineers, we are molecular engineers. So we build a nano car, you see, 2 meter, 2 nanometer, 1 billion times smaller. And it is a 4-wheel drive. Now you might say, this is cool. These students, when I finish high school and I go to the university, they play. Yeah, that's what we do. We play with molecules and we build a nano car. But not, of course, because we wanted to have a nano car. What we wanted is to see if we could get rotation into translation. If we rotate, can you move like a real car at the nanoscale? That was the fundamental question that we asked. And we built it. Here it is. You see the nano car, 2 nanometer, and it moves. And now, if you lift your arm, realize there are these protein motors that make it possible that you can lift your arm. Yes, please do it. Yes, that's great. Millions and millions of nanomotors make that possible. But they don't move like a car on the street or so. It's a different way, a different world. And so probably they move like this. So it walks over the surface. This is probably how it works. And so we built this nano car, and now we're building nano roads, my students, to make much more direction to the movements. And so this was the first electric car, as far as I know, that was ever built in the world, in 1835. It took a few years before we can build a modern Tesla. And most of you will have an electric car in the future, because that's our future, electric cars. This is my cars here. This is what my students made. You see this tiny powder? These are 1 million times a million identical nano cars. 1 million times 1 million. Our car manufacturing plant is not so bad after all. Of course, they are really tiny. So there was also a nano car race. This was in Toulouse in 2017. You see here one of the, with our motor. This is made by James Tour. And there was a real nano car race. It lasted 36 hours. And the Tour Grill team won the nano car race. So as my time is coming, I have few minutes left. Let me just show you one more example, because I got all the questions all the time. Can you move something in your body? And so we thought, can we make a submarine? And then we had the question, my students, we discussed this, what would be a good fuel? Now, your body is full of sugar, So we thought, let's take sugar. And so we built it. We built nanotubes that can convert sugar. This is sugar water. You see these tiny tubes here? The bubbles that come off is oxygen. It burns sugar. And it moves autonomously. I don't have to touch. So we have now these tiny spiders made of these nanotubes. They go like a rocket or a submarine, and they move as long as there is sugar. If the sugar is gone, it stops. When there is more sugar, it moves again. It's like a bit this fantastic voyage. I don't know if you know that. The older people here remember this beautiful book of Asimov and the fantastic film, where they had this spaceship and they shrunk it to micrometer dimensions, and then they injected it and it went to the brain to remove a clot or so. This is nanotechnology, and this is autonomous movement with sugar as a fuel. Catalysis. It's catalytically converting using enzymes. The enzymes that Professor Arnold was talking about. So will we have nanorobots in the future? I don't know. I feel like a baby, eh? We can make just the first few steps, and it's very primitive. But now my students engineer these submarines to make it moving more in a direction, to transport something and so. In the future, yes, I think not today, not tomorrow, but maybe in 50 years, the doctors will inject these nanorobots in your body to do a repair or detect a tumor cell or deliver a medicine precisely on the spot. But I'm not good in prediction, so I would say the best way to predict the future is to invent it. And this is what we as scientists will do, and this is what you are going to do, to invent our future. I couldn't invent anything. Sorry, let me just go back. I talked with you about looking at Mother Nature, looking at all these dynamic functions, that we can move, that we can talk, building switches and motors. And in the future, talking about the future here today, we will have smart drugs, responsive materials, molecular machines, soft robotics. Robotics will, of course, be a big area in the future. We all know that. And you will all be confronted with that. But of course, it's my students who did the work. These are my heroes. I share a passion with these young stars that made it all possible that we can invent our future. And I want to finish today with one or two messages which I experienced being a student like you. And that is, discover your talent. Follow your dreams. That's my most important message. Everybody here is enormously talented. Follow your dreams. Be confident and don't give up too easy. And please discover what is your passion. What does give you energy? And discover your limits. Don't make it too easy. Sometimes it's good to fight for something. Discover how high can you set the bar. But most important, when you go to the future, follow your dreams. And if you think there's nothing to discover because all these professors here have discovered everything, remember these words of Francis Bacon. There are ill discoverers that think there is no land when they can see nothing but sea. The future is yours. And that is why I want to finish with my hero, Leonardo da Vinci. Last week, the French and Italian president memorized the day that Leonardo da Vinci died 500 years ago, exactly 500 years ago, last week. He is, of course, a great hero. And he wrote 500 years ago a message for all of us. Look, where nature finishes producing its own species, man begins with the help of nature to create an infinity of species. Yes, there are a lot of questions and a lot of important problems, but we are going to solve them together. You are going to do that. And so, please don't forget, especially the young people here, imagine the unimaginable. I thank you very much.